Okay, let's start. Welcome to the NTP seminar. And today we are having a talk by Tommaso Macrelli, and he will speak about color-kinematics duality, double copy, and homotopy algebras. So please start.
Thank you very much for the very kind invitation. So today I want to discuss color-kinematic duality, double copy, and their relation with homotopy algebras. After an introduction on color-kinematic duality and double copy and an introduction on homotopy algebras, I will show you how we can realize color-kinematic duality and double copy prescription at the Lagrangian level. And we will interpret this in terms of homotopy algebras. This formulation of color-kinematic duality and double copy would be useful to extend the validity of color-kinematic duality and double copy from tree to loop level. And this is based on the paper mentioned here in this title page that I wrote in collaboration with several people: Liron Borsten, Branislav Jurcho, Jungro Kim, Chris Manzeman, and Martin Wolf. So, first of all, let's consider a very simple example. We consider standard Yang-Mills theory. This is Yang-Mills action, as everybody knows. And the fundamental field of this theory, the gauge potential, has two indices that manifest very different things. We have a gauge index that manifests internal symmetry, the gauge Lie algebra, and the Lorentz index that manifests the space-time symmetry of the theory. And these two indices has in principle nothing to do with each other. And this is what Coleman-Mandurah theorem says. More precisely, we have that under very general assumption, the most general symmetry algebra that of our quantum field theory that leaves its S matrix invariant is the direct product of the space-time symmetry algebra and the internal Lie algebra. And I am excluding supersymmetry from this statement. And so the space-time index, the space-time Lorentz index, and the color index cannot combine in any but the trivial way. Well, a modern perspective on gauge theory apparently, just apparently, seems to challenge this result. And this perspective is indeed given by color-kinematic duality. So again, let's consider our main example, Yang-Mills theory. And let's consider the 4.3 level scattering amplitude of the theory. This is given in terms of a sum of trivalent graphs referring to the interaction channel S, T, and U, and the quotic vertex contribution. Now let's consider a trivalent graph, for example, the S channel. We can factorize the numerator for the expression for this Feynman diagram into two terms. The first bit is composed of gauge group structure constant, while the second bit is composed of Lorentz invariant contractions of polarization and momenta. We call the first one the color factor, CS, and the second one the kinematic factor, NS. And we can do the same thing for the other interaction channel, T and U. Coming to the quotic vertex, we can do the following thing. We can take the quotic vertex and blow up this vertex into trivalent contribution. According to the color structures, we will then split this contribution to the different interaction channel. The aim of this procedure is to rewrite the 4.3 level scattering amplitude for Yang-Mills as a sum of purely trivalent graphs. So we blow up the 4-point vertex in this way, and we rewrite the amplitude in this way, where we split it according to the various color factors, the kinematic contribution coming from the 4-point vertex. And so we have redefined the kinematic factors appearing in this formula. Now, looking at this formula, we have that the color factors satisfy the standard Jacobi identity. And indeed, this fact implies that the 4-point 3-level scattering amplitude is invariant under the following shift, the following transformation for kinematic factors. So this is what we will call in the following generalized gauge transformation. And it tells us something really important. That is that the kinematic factors are not uniquely determined by the scattering amplitudes. Secondly, we have another very important observation that kinematic factors satisfy the same algebraic identity, namely Jacobi identity, satisfied by the respective color structure, and we call it kinematic Jacobi identity. And it is the last equation of this slide. Now, this thing at 4-point was already known even before color-kinematic duality was formulated. We can extend the validity of this observation in some generality. So let's consider an n-point L-loops Yang-Mills amplitude. Using the same trick of blowing up the 4-point vertex, we can rewrite this amplitude as a sum of trivalent graphs, trivalent contributions. And in this formula, we have here some symmetry factor. We are integrating over the internal momenta, circulating in the loops. We have denominator coming from propagator. And the most important part of the integrands for our aims is the numerator. We can again split this numerator into 2 bits. The red one is gauge group structure constants, and this is what we call the color factor. The other one is the kinematic factor, Lorentz invariant contractions of polarization and momenta. Okay, and again, we have that the kinematic factor is not uniquely determined. We can shift the kinematic factor, and if this shift satisfies this relation, we have that scattering amplitudes are invariant. And this is something, the fact that the kinematic factor is not uniquely determined by this formula lies at the heart of the following statement. That is, the color-kinematic duality as originally formulated. So there is a choice of kinematic factors such that they obey the same algebraic relation, antisymmetry, Jacobi identity, of the correspondent color factor. This is surprising and incredible on its own, but if it is true, it would imply something really powerful. We can use this statement to compute gravity amplitudes from Yang-Mills 1. So this is proven to be true at 3 level, and it was only conjectured for loops. And if this is true, if color-kinematic duality holds true, then we can replace in this formula in the trivalent graphs reformulation of Yang-Mills theory, we can replace the color factor with a copy of the kinematic factor. We obtain a new expression, and the double copy prescription says that this expression is a legitimate gravity, or better, n equals 0 supergravity amplitude. N equals 0 supergravity is just Einstein-Hilbert gravity plus Kalb-Ramond theory plus dilaton. It's the universal NS sector of closed string theories. So this is a no-loop statement. It holds in full generality. The problem is that to validate the double copy prescription at a given loop, we need color-kinematic duality to be valid at that given loop. Until now, what I exposed was purely an on-shell scattering amplitude story. Now I want to change the perspective. I want to switch to an off-shell Lagrangian realization of color-kinematic duality and double copy prescription. Since this is the road we will take to solve the loop problem. the first step in this direction is an existing equivalent action for Yang-Mills theory that was first computed in one of the original paper by Byrne and collaborator, and then was algorithmically constructed completely by Tolotti and Weinzel 3 years later. So this equivalent Yang-Mills action manifests three-level color-kinematic duality for on-shell physical gluons. And this action is precisely the standard Yang-Mills action plus an infinite number of extra contribution. Now, this extra contribution are actually zero. So this is really, from the point of view of computing this action, this is really Yang-Mills amplitude. We are adding zero, but this is an elaborated zero. The contribution that we add, indeed, when we compute the diagram associated with this action, allow us to split the total vanishing contribution into a partial contribution that, according to the color structure, goes in the different interaction channel, and allow us to rewrite the scattering amplitude in a manifestly color-kinematic dual form. For example, this is the quintic term of this Tolotti and Weinzel action. You can see that when you enforce Jacobi identity, the expression inside this big round bracket actually vanish. But keeping this expression and computing diagrams from this action, having this contribution allow us to split according to the various color structure, the contribution that is totally vanishing, but it's not vanishing when we split it into each interaction channel. And so we obtain a color-kinematic dual parameterization of the scattering amplitude. Now we want to solve two of the issues of this action. This action has an infinite number of terms. It contains arbitrary vertex of arbitrary high order, and it is non-local. So first of all, we can always put an Lagrangian field theory in a form, a polynomial Lagrangian field theory in a form where the interactions are at most cubic. This follows from general homotopy algebra argument, namely the Strictification Theorem. And this is why this procedure, we refer to this procedure as strictification. But we will see this in a much more field theoretic way here. And this is a shadow of this general result at the level of homotopy algebras. So the idea is just to insert auxiliary field to strictify, to make the action at most cubic. Let's consider, for example, an action with a quintic term expressed in terms of some structure constant related, say, to a lead algebra. And we have the following quintic term, where we have here field and here structure constant. Now, the structure constant implies a particular diagram structure for this term. And the particular structure implied by the structure constant tell us how to proceed with strictification. Indeed, we introduce auxiliary field, two couple of auxiliary field, to make this quintic term cubic. Indeed, when we integrate out in the last expression of this slide, when we integrate out the auxiliary field, what we find is that we recover precisely this quintic term. In an analogous way, using introducing auxiliary field and integrating them out, we can show that non-local terms of this form that we encounter inside Tolotti and Weinzel action can be made local with the introduction of auxiliary fields. And again, this is proven just integrating out the auxiliary fields. So Using this technology, what we can write is a reformulation of Tolotti and Weinzel action, this time local, and that contains at most cubic interaction. In general, the price to pay for doing this is the introduction of an infinite tower of auxiliary field. But since every consideration we will formulate is perturbative, we will be interested only up to a certain number of external legs. And so we will need only a finite subset of the auxiliary fields. And so we can write a local cubic theory that, just like Tolotti and Weinzel action, manifests Colour-kinematic duality for on-shell physical gluons. But we want more, since we want to use this Lagrangian formulation to address the problem of loop-level Colour-kinematic duality and double copy. But in principle, we can have violation of Colour-kinematic duality coming from unphysical polarization of the gluons and from ghosts. We plan to compensate for this violation, introducing a suitable choice of gauge and with field redefinitions. And Batalin-Vilkovisky formalism, or for short PV formalism, is the right framework where we want to work, since it allows us to work with very general gauge choices. And it naturally provides a link with homotopy algebras. That would be a good language to understand Colour-kinematic factorization at the level of at the Lagrangian level. So I start here introducing homotopy algebras in a very basic and informal way. So homotopy, we can think of homotopy algebras as generalization of the classical algebras we all know, for example, the algebras.
Sorry, can I ask a question?
Yeah, sure.
Could you please return to that slide with the local Lagrangian? And could you please explain again, like in what way it makes Colour-kinematics duality manifest, and why only on shell?
Well, this construction was performed in Tolotti and Weinzel paper. The idea is the following. We are adding to Yang-Mills Lagrangian a contribution that is actually zero. For example, if you look at this quintic term, when you enforce Jacobi identity, this is zero. But again, having this term, when we write the diagram, when we factorize the contribution according to the various color structure that appear, we have the total contribution that is vanishing split into several contributions. And the several contributions that are not vanishing provide parametrization of, in this sense, of the Yang-Mills tree-level scattering amplitude that is Colour-kinematic dual. The total contribution is, of course, vanishing. We are doing something like this, like a generalized gauge transformation. And we are not changing anything in the total amplitude. We are just arranging the various partial contribution that sums up to the total amplitude in a way that they are Colour-kinematic dual. And there is an algorithmic way to produce this Tolotti and Weinzel action. Actually, on their paper, the first steps are already performed in Bernden and Huang paper, and then Tolotti and Weinzel constructed an algorithm to write for arbitrary n this action, and this is, in a sketchy way, the general expression that you have at order n.
And then why does it fail for off-shell fields?
Well, their algorithm take in account only tree-level scattering amplitude with so on shell and with gluon as external particle, is let's say an input. I think of, we can say it is an input of their construction. They wanted to make manifest only 3 level. To extend this to the loop level, we have, of course, not only to consider the physical gluon, but unphysical polarization of the gluon and also the ghost. So everything that can appear inside the loop. And this would require much more work. And I will address this point after the introduction on homotopy algebras. And indeed, this is our step that realize the color-kinematic duality for the BST extended field space.
Thank you.
Thank you for your question. So,
sorry.
Oh, sure.
It's basically the same question, because I thought you want vertices in a cubic form, but this action you showed, the non-local one, it's not cubic.
No, this
How
action
it
is
makes
not cubic.
anything manifest.
This action is not cubic. The step to make this action cubic is indeed the strictification. As I showed in the slide, you can, and this is something general, valid for every polynomial action. Say that you have, for example, a quintic term like this. You can always write terms of this form as sum of trivalent cubic at most contribution. And we do this inserting auxiliary field. When we consider the last expression of the slide, where I have introduced a couple of auxiliary field, and when we integrate out the auxiliary field, they are just algebraic auxiliary field. So when we start the equation of motion of the auxiliary field, we see that this cubic expression recover the original quintic one. And this is something that can be done for every polynomial term that appear in the action. And this is consequence of a more general result at the level of homotopy algebra. And so the steps are the following. We start with this action that manifests color-kinematic duality for 3-level physical gluon. Then we can strictify this action. For example, we will obtain a cubic theory with auxiliary fields, and this cubic theory again would manifest color-kinematic duality on shell and for physical gluon. To extend the validity of color-kinematic duality, the BST extended field space, I will show this in the following slides after the homotopy algebra introduction. There is some work to be done.
Yeah, okay, many thanks.
Okay. Okay, other questions? Okay, I go on with homotopy algebras. So as I said, for example, let's consider a Lie algebra. How to obtain the homotopy generalization of a Lie algebra, that is what we call an L-infinity algebra. We consider the structural identity of the algebra, that is Jacobi identity. And we require that the structural identity of the algebra is violated. And this violation is controlled by an homotopy. So in the case of Lie algebra, we have Jacobi identity, and Jacobi identity for L-infinity algebra would be violated, and its violation would be controlled by an homotopy. I will describe this in detail in the following slides. And in this way, we can generalize the associative algebras, commutative algebras, Lie algebras to their homotopy algebras counterparts, A-infinity, C-infinity, and L-infinity algebras. The structures appear in various places in theoretical physics. For example, the algebraic structure of classical closed string field theory is an L-infinity algebra. And in general, under every Lagrangian field theory, there is an L-infinity algebra that codifies the complete classical theory. And the bridge between the theory and the associated L-infinity algebra is Batalin-Vilkovisky formalism. BV formalism is a formalism that was developed to gauge fix and quantize complicated gauge theories. To quantize a theory for me means to make sense of the path integral. We know that usually this object is LBA, and the standard approach to cure this illness is BST formalism. BST formalism for standard gauge theory, for Young's theory, for example, is enough, but this because the symmetries of the theory close off shell, or in other terms, because we have a BST complex that is a complex also of shell. But we can have more complicated example of gauge theories, like higher gauge theories, where the BST complex is a complex only up to equation of motion. And to proceed with quantization, we want an off-shell complex. And this is realized at the level of BV formalism. So BV formalism, BV procedure is a two-step procedure. In the first part, we introduce parameters to parameterize gauge freedom, just like in the BST formalism. We introduce ghosts to parameterize gauge freedom, and in case of high gauge theory, where ghosts may enjoy themselves gauge freedom, we introduce higher ghosts. And this is just the construction of the BST complex. Then the following step is that we double the field content of the theory. To every field, ghost, high ghost, we introduce an anti-field, an anti-ghost, a higher anti-ghost. And the structure that we obtain is a cotangent bundle that comes with a natural symplectic structure. And so we can define Poisson brackets. And we use these Poisson brackets to define new objects that generalize the old BST ones. So we define a BV operator and a BV action, and we require that when we compute this object on the old BST field, we recover the old BST object, the BST operator and the BST action. The last equation of this slide generalizes the notion of gauge invariance for the action in the BV formalism, and is known as classical BV master equation. Now we have that in terms of QBV, we have a differential complex, we have a differential algebra, and this algebra dualizes to a codifferential coalgebra that can be equivalently described as an L-infinity algebra. But
it's only correct formally, right? If you expand in fields. So if you have a non-trivial geometry of your field space in BV, it's not fully captured by linear structure by L-infinity, right?
It's
a perturbative expansion. L-infinity is just a jet of differential.
Is your what you're saying is that homotopy algebra capture just the perturbative theory? If this is what you said, then the answer is yes.
Yes. Yeah, sure. Yeah.
Thanks. Okay. Yes. Homotopy algebras capture just, yeah, this is an important point. Thank you for the remark. Homotopy algebras capture just the perturbative theory. We're indeed interested in the perturbative aspect of Colour-kinematic duality and double copy. So every consideration we will do is perturbative. Okay, thank you very much for your remark. So, but before going to L-infinity algebra, let's just conclude the discussion on BV formalism, since the original aim of BV formalism is quantization. Before quantizing, we need some gauge fixing condition. And in BV formalism, to gauge fix means to evaluate the action on an appropriate Lagrangian submanifold. In practice, this is performed introducing a gauge fixing fermion, and we eliminate, say, the unphysical degree of freedom, taking functional derivatives of the gauge fixing fermion in the way depicted in the slide here. And then we have to ensure that the expectation values for observables is gauge independent. And this leads to a generalization of the classical BV master equation called the quantum master equation. And it is the last expression of the slide. First bit is the classical master equation. Then we have a second term featuring h bar, and this delta BV, that is the BV Laplacian, and it is a second order differential operator that contains one functional derivative with respect to field and one functional derivative with respect to antifield. So this is just a summary of what we have done. So we started with a gauge theory, or a higher gauge theory, and then BV procedure is a two-step procedure. First, we introduce the BST complex. We parameterize gauge freedom with ghosts and eventually high ghost for high gauge theory. Then we double the field content of the theory, and we are ready to gauge fix and quantize. So, as I promised, I will go to the dual picture now. BV formalism, but also BST formalism, introduce a differential on the algebra of polynomial function of the fields. And this is an instance of a more general geometric construction, where we have an homological vector field over some graded vector space. And this is what we call Q vector space. The simplest possible example is the one where we have an ordinary vector space, and the most general degree 1 differential that acts on the algebra of function of field is given by this expression in the center of the slide. And psi are the coordinate function, that is the dual basis of the dual vector space. And it is given in terms of some structure constant. Now, if we require that q squared to 0, then this is equivalent to require Jacobi identity for the structure constant. In other terms, requiring that q squared to 0 is the same to require that we have a Lie algebra structure on the original vector space. We can see this duality in a very compact way, introducing what are called contracted coordinate functions, that are just the tensor product between the dual basis and the original vector space basis. Now we can act with Q on this contracted coordinate function, Q act on the dual basis on the coordinate function. And this action dualize in this way, as I had described, to Lie brackets. Now, the general case that is the relevant case for BV formalism is the one where we have a graded vector space. And we have our Q that is QBV. This time, we can always write contracted coordinate functions and think of the action of QBV on them. But this action would dualize to something more complicated than Lie brackets. Indeed, we obtain on the other side a sum of multi-brackets that are multilinear graded antisymmetrics, and we will call them higher products. And requiring that QBV squared to 0 is equivalent to require that this higher product satisfy a generalization of Jacobi identity that we call homotopy Jacobi identity, that is the structural relation of an L-infinity algebra. In this way, to every Lagrangian, polynomial Lagrangian field theory, we can associate an L-infinity algebra using the BV formalism. And this L-infinity algebra will capture the complete perturbative theory. Now, this is an example of this formalism applied to the familiar Yang-Mills action. So this is a Batalin-Vilkovisky Yang-Mills action. The first term is the familiar Yang-Mills action. This is pure Yang-Mills. And then we have terms featuring antifields. We have here an anti-gluon, here a BV anti-ghost. And the last term is a bit tricky. As I mentioned, for quantization, we need to introduce a gauge fixing fermion. Now, this gauge fixing fermion is a degree -1 field. To build this field, we need additional fields that should not ruin the BV complex. And so, in that sense, they have to be trivial, and we will call them trivial pairs. The fields that appear in this last term are indeed trivial pair fields. Now, we want to reformulate this action inside what is our general template to cast every polynomial action we are interested into. That is homotopy Maurer-Cartan theory. So let's consider an L-infinity algebra. Let's consider a cyclical infinity algebra. That is an L-infinity algebra endowed with a bilinear pairing, that is cyclic in the usual sense. We can associate to this cyclical infinity algebra a Maurer-Cartan homotopy theory. That is a theory expressed by this action here. We have here the angular bracket that are the cyclic structure, this kind of inner product, and mu I that are the higher products of the L-infinity algebra. And what we can do is to reformulate every action we are interested into, for example, Yang-Mills theory, as a Maurer-Cartan theory. So this is the first product of the L-infinity algebra associated to Yang-Mills theory. We have here ghosts mapped to gluon, mapped to anti-gluon, mapped to anti-ghost. This captures the kinematical part of the action of Yang-Mills action. And here we have trivial pair fields that are indeed trivially mapped into each other with the identity. And this is mu1, the first product of the L-infinity algebra. Then we have a set of all the non-vanishing higher products for Yang-Mills theory that reproduce the interaction vertices. And endowing the structure that is an L-infinity algebra with the following cyclic structure, we have a cyclical infinity algebra, and the associated Maurer-Cartan action is indeed a Batalin-Vilkovisky Yang-Mills action, this action here. And in this way, we can read the L-infinity algebra associated to the field theory from this Maurer-Cartan homotopy theory. Now, for our purpose, we need a very special, family of gauges. The gauge fixing fermion we will consider is of this form, where psi is a real parameter. This is what is called, I think, an arXiv gauge. Then we gauge fix the action. And the gauge fix action is expressed by these formulas here. We are choosing this particular gauge fix just to reveal at the level of the Lagrangian the factorization between color and kinematic. This will be clear in the following slides. Again, to make manifest this color-kinematic factorization, we consider this field redefinition for Yang-Mills theory. What we obtain is this field redefined action that is closely related to what we want to get in the end. Here, I've written only the kinematic part of the action. The associated chain complex mu1, the chain complex associated to the mu1, the first product of the L-infinity algebra, is the following one. And this, as we will see in the following slide, this is almost what we want, something that we can interpret as a tensor product. But we have here this cross term. Keep them in mind, since they will ruin the idea of writing this thing as a plain tensor product. We will need to twist this tensor product. But speaking of homotopy algebras, we don't have a notion of tensor product between arbitrary homotopy algebras. Let's make a step back and let's consider the classical algebras. This little table summarizes the available tensor product between compatible classical algebras and what kind of algebras is the result of the tensor product. And for two compatible algebras, we have this formula here for the product. Next, we have a notion of tensor product at the level of chain complex. For chain complexes, tensor product is given by these standard formulas. And this is the differential on the tensor product. Now, as I said, there is this important structural result for homotopy algebra called Strictification Theorem. Every homotopy algebra is equivalent to a strict homotopy algebra. That is, an homotopy algebra with only the first two products, mu1, the unary product, and mu2, the binary product, that are non-vanishing. And this is indeed why I said that at the level of homotopy algebra, the strictification result implies that every Lagrangian field theory can be reformulated as a theory with at most cubic interaction. But a strict homotopy algebra is nothing more but a differential graded algebra. And since we have notion of tensor product between algebras and between chain complexes, we can use this formula to generalize the notion of tensor product to strict homotopy algebras. And we will have an analogous compatibility table for the tensor product of strict A infinity, C infinity, and L infinity algebras. So this is the notion of tensor product between strict homotopy algebras we want to use. Now we want to factorize Yang-Mills theory. We will factorize Yang-Mills theory into a color and a kinematic bit, and also a scalar bit. So scalar is the A infinity algebra of a cubic scalar theory. It's really, it will really provide the bone of the diagrams of the theory. Next, we have color, that is simply the gauge-Lie algebra of the gauge theory we are considering, and then kinematic. Kinematic is given as a graded vector space spanned by a basis that corresponds to the Poincaré representation of the fields of our theory. Since this is already the strictified Yang-Mills theory, we, aside the usual ghost, gluon, Nakanishi Lautrup, anti-ghost field, we will have also an infinite number of auxiliary fields. And so the basis will correspond, the basis element for kinematic will correspond to Poincaré representation of ghost, gluon, Nakanishi Lautrup field, BRST anti-ghost, as well as the Poincaré representation of the tower of auxiliary field we need to strictify the theory. You can see here that the product between kinematic and scalar is not an ordinary tensor product in the sense that I have explained it in the previous slide. It is what we call a twisted tensor product. The reason is that to recover these cross arrows, we need some twisting, and we want that kinematic, that is just a graded vector space, acts like a kinematic operator algebra on the scalar part of the theory. So this twisted tensor product is defined by the introduction of a twist datum that simply says how the kinematic part act in an operatorial way on the scalar part. And the expression for the unary and binary products in terms of this kinematic, of this twist datum, are the last two equations of this slide. And the twist datum would be completely dictated by the field theory we consider. At this level is something ad hoc that we introduce for Yang-Mills theory, but we will fix once and forever here. So let's consider the kinematic part of Yang-Mills theory. So the scalar, the kinematic part of the scalar factor is just given by this chain complex. We have fields mapped to anti-fields, and mu1 is the box operator. And then the twist datum we need to reconstruct the Yang-Mills theory is explicitly given by these formulas. Using all these elements, what we obtain is precisely this an infinity algebra that reproduces this kinematic part of field redefined Yang-Mills theory. Now, we want to factorize the full interacting theory in this way. And to do so, we need a strictification of Yang-Mills theory, not an arbitrary strictification. We need a strictification that manifests Colour-kinematic duality, possibly of shell. And this is a nice observation. On one hand, we have the fact that from practical reason, we have a notion of tensor product between strict homotopy algebra. We want to work with strict homotopy algebras. On the other hand, we have that Colour-kinematic duality and double copy are actually tied with cubic reformulation of the theory. This is just, yeah, an observation. So let's pick up the discussion on the strictification of Kennedy's theory from where we left it. That is at the Tolothian bind selection chapter. So as I said, scattering amplitude with external arbitrary polarized gluon can ruin, in principle, Colour-kinematic duality. We can have Colour-kinematic violation, and to compensate for them, we need terms proportional to partial mu a mu in the action. Now we can generate these terms, thanks with an appropriate choice of gauge fixing and redefining the Nakanishi output field. Now we will we will compensate this violation of Colour-kinematic duality in a recursive way. We start tree-level 4-point, and we start by considering violation coming from unphysical polarizations of the gluons. So we discovered that at 4-point, the relevant correction that we can produce with the OR gauge choice and the redefinition, the shift of the Nakanishi output field, the correction that amends for Colour-kinematic violation from arbitrary polarized gluon is the following one. This is 4-point in the action. And we can generate this term in this way with field redefinition. Next, we want to consider also ghost. Since we want to extend our consideration to loop level, we want to consider scattering amplitude with external legs that are pair ghost, anti-ghost. And they can also ruin, in principle, Colour-kinematic duality. We then use on-shell word identity to relate scattering amplitude with a certain number of pair ghost, anti-ghost, with scattering amplitude with a lower number of pair ghost, anti-ghost. And in this way, we can relate, for example, at 4-point, the scattering amplitude with a pair ghost, anti-ghost, with a purely bosonic scattering amplitude. And in this way, we can compensate for violation of Colour-kinematic duality coming from ghost, anti-ghost pairs. At 4-point, explicitly, we discovered that no autocorrection of Yang-Mills Lagrangian are needed. So at 4-point, this is the only contribution we need. So, for example, at this point, we can strictify the Yang-Mills Lagrangian. What we can obtain, what we obtain is a cubic theory that manifests Colour-kinematic duality, again on shell, but for the full BST extended field space. And at 4-point explicitly, this is the expression for Yang-Mills Lagrangian. And we have introduced here, to strictify the theory, a bunch of auxiliary fields. Now, but we want to do more. We want to lift the Colour-kinematic duality from on-shell to off-shell. So off-shell, the only possible violation of Colour-kinematic duality should be proportional to p squared, where p is a momentum, is the momentum of an external field. So this term can be compensated order per order with terms in the action that are proportional to the equation of motion of the fields. Again, we can generate these terms, but with a field redefinition that in general would be non-local. Now, considering non-local field redefinition leads to an equivalent theory. The problem is that the Jacobian determinants will lead to additional counter term, and we need to consider these counter terms for the full scattering amplitude and for the renormalization. Now we will be interested only in the loop integrands. So, and this is an important point, we're interested in color-kinematic duality only for loop integrands. Loop integrands are not physical quantities. And we will say nothing at this level on color-kinematic duality for contour terms and color-kinematic duality for the full integrated amplitude. So we restrict our attention on color-kinematic duality only for loop integrands. So in this way, we produce a new action that manifests for loop integrands color-kinematic duality of shell. And we can strictify this action up to the relevant order we are interested in. Now we have obtained a strictification of Yang-Mills theory that manifests this factorization, and that is color-kinematic dual. And we can consider the double copy of this theory. At the level of homotopy algebra factorization, double copy is realized in this way. We have here Yang-Mills theory, and we can substitute a factor with a copy of the other factor. For example, we can substitute kinematic with a copy of the color factor. What we will obtain in this case is a bi-adjoint scala theory. But we are interested into the other direction. That is, we want to substitute color with a copy of kinematic. We will obtain a new theory. We have to prove that this theory is in some sense consistent, and we want to prove that this theory is indeed n equals 0 supergravity, at least perturbatively. So we start with our cubic theory that manifests the color-kinematic duality of shell for loop integrands. And we write also the BST operator associated to this theory. Now, we want to double copy both action and BST operator. So really what we do is to replace every structure constant and every color structure constant and index with a copy of kinematic structure constant and index. And here I have highlighted with red the color structure constant and with blue the kinematic ones. So we replace color structure constant with kinematic structure constant. We obtain a new theory and a new BST operator. Now, this is what we have obtained consistent. You know that if we have BST operator that's square to 0 and an action that is invariant under the new BST transformation, the answer is, if we have that the kinematic structure constant satisfy the same algebraic relation of the color structure constant, then yes. And this is indeed equivalent to require off-shell color kinematic duality. So we can double copy. And we take Yang-Mills theory, formulated in that way, we double copy the theory, and the field content of the double copy theory is the following. We can organize it in an antisymmetric and asymmetric sector. The antisymmetric sector is the following one that will be related, a little spoiler, to Karl-Bramond theory. And the symmetric sector is this one. It will be related to Einstein-Hilbert gravity plus dilaton. And then we have an infinite number of auxiliary fields. And the action, here I show only the kinematic part of the double copy action, since it's a really lengthy expression, even considering only the first interaction terms. The double copy action has the following form. This is the antisymmetric sector, and this is the symmetric sector. Now, the first step to show that this perturbatively describe n equals 0 supergravity is to show that the antisymmetric sector and the symmetric sector are related respectively to Karl-Bramond theory and Einstein-Hilbert plus dilaton. And so we focus first on the kinematic part of the action. So the antisymmetric sector is related to Karl-Bramond theory by the following field per definition. And we have analogous expression that I omit here in the slide since they are lengthy. You can see them on the articles. for Einstein-Hilbert gravity plus dilaton related to the symmetric sector. And then if we integrate out the auxiliary field, we have two theories with the same field content and the same kinematic terms up to field redefinition. And it's important to stress that the field redefinition here relates the linearized PST operator that we have on the double copy theory and n equals 0 supergravity. Now, an input of this proof is that the three-level double copy holds. Then if we set the unphysical field to 0, we have two theories that are classically or better semi-classically equivalent. Again, we want to extend the validity of double copy to loop level. So we have to consider gauge fixing sector and ghost sector. So using techniques similar to the techniques implied before, we can redefine the gauge fixing sector and use word identity in the way I showed you before to extend this result to the full BST extended field space. Now, if we integrate out the auxiliary field, we have that the discrepancy between the two actions should be proportional to the equation of motion of the fields. This should not be visible at on shell. Such differences, again, can be produced with eventually non-local field redefinitions. And so what we obtain is that the action for the double copy of Kennedy's theory and the action of n equals 0 supergravity now matches. And the discrepancy is at most a trivial symmetry. And so in the end, we have showed that at least perturbatively, Yang-Mills double copy and n equals 0 supergravity describe the same theory. So there are many possible directions to apply this formalism. Something that we will do in an upcoming paper is to clarify the mathematical structure of this color-kinematic factorization in terms of homotopy algebras, or twist the tensor product, capture the physical aspect of the construction theory, but it's somehow not very natural from the mathematical point of view. And we want to give a more precise, more elegant in terms of homotopy algebra description of this color-kinematic factorization. Then we can use this Lagrangian approach to color-kinematic duality and double copy to study a wide range of theories. There are several theories where we have color-kinematic duality and several double constructible theories. For example, another theory that we study with this formalism is nonlinear sigma model. Nonlinear sigma model exhibit flavor kinematic duality, and its double copy is the special Galilean. And we can also consider gauge theories with supersymmetry that double copy to supergravities. Then it will be very interesting to address renormalization and counterterm, something that we didn't address it, with this approach. We only focused at the level of loop integrands. And finally, since ultimately, at least at the tree level, the double copy prescriptions should come from a duality between open and closed string amplitude, it would be relevant to study with our homotopy algebra technique KLT relation that are intrinsic to tree level, and maybe try to extend the validity of this relation to loop level. So this is everything I want to say. Thank you very much for your attention.
Thank you. Are there any questions?
I wanted to ask, can I?
Yeah, sure.
Okay, so I wanted to ask, you talked about homotopy algebras, and you said that that like Jacobi identities hold up to homotopies, and you said that it will be explained later, but maybe I missed it.
Okay. in the context, let's consider, for example, L-infinity algebra that are the generalization of the algebra. You have for L-infinity algebra, second that I go to the relevant slide, okay. You have the fact that q squared to 0, that on this side is equivalent to a complicated expression, that is what we call an homotopy Jacobi identity. And it's something that we can split in several components. For example, the first Jacobi, the homotopy Jacobi identity simply says that the mu1 squared to 0 is a differential. The second one says that...
No. This part I understand. So if you have L infinity, you have these multilinear products that they take like n elements of L to L. And but I don't understand how is this related to homotopy?
The homotopy part. Well, the Jacobi, the standard Jacobi identity, that is the third component of this homotopy Jacobi identity, is precisely on the left-hand side Jacobi identity, and the violation of the Jacobi identity would be something like mu1, mu3, a, and mu3 is the homotopy that controls the violation of the standard Jacobi identity. I didn't wrote that explicitly. I'm sorry for this. You can, for example, refer to the long paper on L-infinity algebra for the explicit expression.
Okay,
but
thank you. Thank you.
Thank you very much for your question.
Other questions? Can you explain why using this BRSC BV was essential here? So could you just, let's say, add that like action that you started from terms proportional to containing extra polarizations, etc., without using BV?
Okay. Well, using BV algebras gives you a direct connection with homotopy algebras. And also, BV formalism allow you to consider more general gauge fixing condition. And we want to work with a particular choice of gauge, since to make manifest the color-kinematic duality and double copy prescription, an explicit choice of a particular choice of a family of gauge is required. And we also want to give a connection with homotopy algebras. And so working with the BV formalism is the natural thing to obtain these two goals. But actually, the double copy from the Lagrangian BST perspective can be described also without BV formalism, aside for minor remarks. For example, the first paper here makes almost no use of homotopy algebra techniques. But we wanted to use BV algebra, for example, to interpret in this way color-kinematic factorization. And in an upcoming paper, we will give a more homotopy algebra focused perspective on color-kinematic factorization.
Thank you. You also suggested at the beginning that all this discussion violates Coleman-Mandula theorem. In which way?
Oh, well, the fact is that as usually formulated, the loophole that says we are not violating Coleman-Mandula theorem is that color-kinematic duality is not a symmetry of the S matrix. But when we extend the theory, the S matrix to the full BST field space, then yes, it is a symmetry of the metric. But then the loophole is that the inner product that we have on the Hilbert space is not positive defined. And this violates Coleman-Mandula theorem. And also we have an infinite number of auxiliary fields, and this is another loophole for Coleman-Mandula theorem. So we are not violating Coleman-Mandula theorem.
Okay, thank you.
So may I ask a question?
Yeah, sure.
Is it possible to extend this construction by considering Youngman's theory and ADS background, say, as a part of supersymmetric theory?
Okay, so I would say probably yes, but I didn't try it. So I would say that probably one can work with. Here we are in flat-Minkowski, but I think that it is possible to do something similar. I don't see why it wouldn't be possible.
But after all, you need an S matrix, right? Which is peculiar to a flat space.
This discussion here is really at the level of the Lagrangians. So yes, probably there are some conceptual problem. Like, yeah, but this discussion is really at the level of Lagrangian. So from the initial on-shell perspective, we went to an off-shell Lagrangian description of this factorization. And this, for example, yes, can be maybe useful in this case.
Okay, and yet another naive question. So,
yeah, sure.
Do you understand correctly that it's essential to have a non-abelian algebra of global symmetries to have this color-kinematic duality? And for example, say, if we consider electrodynamics, there is no place for such a duality.
Oh, well, for electrodynamic, well, let me think. You don't have Jacobi identity, but still,
Right, that's right.
Yeah, I think yes. It will be, if formulated for Maxwell theory, it will be a trivial statement, I think. Yes.
Okay, it realizes. Okay, but if we consider some nonlinear versions of electrodynamics, like Born-in field,
okay,
or something like that, so is it possible to have sort of this duality there?
I know that there are works on double copy, for example, also using the scattering equation formalism for these theories. So I would say that we can use that this formalism can be used also to study these theories. But I do not precisely the detail of the color-kinematic factorization for these theories. But in principle, yes.
Okay, thank you very much.
Thank you.
So there was a hand raised.
Another question, okay.
Yeah. Do you hear me?
Yeah, I hear you well. Sorry, I don't hear you anymore.
You don't hear me?
Oh, now yes.
Yeah. So Born-in field actually is in the web of the theories related by color-kinematics.
Indeed.
So yeah, that's actually not a huge deal. Otherwise, electrodynamics is a special case of
Yes.
A special case of gauge theory. It's just the Jacobi identity is 0 equals 0. So,
yes, indeed, the trivial thing.
But all of this works, right? QED amplitudes are a subset of QCD amplitudes. You can always get QED from QCD. It's you just need to project color factors. So yeah, that wasn't the question. I was wondering, just to ask you if you have some list of things that you could now produce using this formalism, like.
For example, we can extend this formalism to supersymmetric theories, and this is done. For time reason, I didn't include that part in this presentation.
Yeah.
In this last paper, we generalized this construction to supersymmetric theories, and theories including also fermions.
Well, I rather meant, can you produce numerators that obey color-kinematic duality? Do you have a, because I'm asking because there's a paper quite recently by Chung and
the one that
Langen, and they claim to have produced endpoint numerators in Yang-Mills theory, and they don't use your formulas. So, well, one thing is that can you use your formalism to also produce the same or similar results as they have produced?
This is an interesting question to see if we can reproduce the same result with our formalism.
It doesn't have to be the same.
We didn't try it yet. I know that paper, and if I remember, it also used auxiliary fields. I think finite number of auxiliary fields, something like this. It would be interesting to see if we can reproduce the result.
Well, you don't have to reproduce their result. You just need to produce a closed form formula, a closed form expression for numerators that could be an equivalent result to theirs.
Or algorithmic construction of since we were more interested into the at the Lagrangian level.
Yeah, or the reason why people were interested in the Lagrangian was to have a straightforward way to get those numerators, because the
once you have the Lagrangian, there is an algorithmic way to produce loop integrand. That is the usual fact that from an action principle you can write scattering amplitudes, and indeed this construction produce an action that produce loop integrands with color-kinematic, parameterized in a way that color-kinematic duality is manifest.
Right. So fair enough.
I don't have a closed formula. Let's say a closed formula for the kinematic numerator. Okay.
Okay. Yeah. So, but okay. So at tree level, the existence was known anyways.
Yes. Yes.
But I guess one of the non-trivial questions about loop level is that it's not clear that you can produce those numerators at higher loop orders.
Well, as I said,
can you answer this question? Yes or no?
Yes. Yes. This action, the action that we construct in this way, can produce loop integrands that are color-kinematic dual. As I said, we don't make any assumption on the contour terms and on the renormalization. We are just saying that this formulation of the theory reproduce loop integrands that are loop integrands that produce the same, that are equivalent to the loop integrands of the relevant theory that are color-kinematic dual. Yeah.
Okay. And then an interesting question would be, so your claim is that at any loop order, there's enough freedom in the generalized gauge transformations to find such numerators. The interesting, another quirk that has been observed was that even at loop level, even at 2 loop levels, so not that high number of loops, at I think it was 5.5 gluon all plus at 2 loops. People, well, actually, my collaborators, they've tried to produce those numerators for that amplitude, and they had to go to very high orders in loop momentum. So they had to, normally there is a finite number of loop momenta that appear in the integrand. But to make the Colour-kinematics duality manifest, they had to introduce additional powers of loop momenta into the integrand. So that wasn't very nice. They ended up finding numerators, but they were just too ugly to be happy about. Can you say something about the momentum dependence of loop numerators that you would be producing?
Sorry, let me just formally announce the end of the seminar, and then you are free to discuss.
Sorry, yeah, sure.